Welcome back. So today I would be talking about Phantom Zone. But before I sort of like dive deep into Phantom Zone and talk about the rest of the things, I would sort of walk you through the motivation behind Phantom Zone. So if you guys are familiar with globally mutually trusted third party, I would want to introduce you to this idea of globally mutually trusted third party. What is this globally mutually trusted third party? Well, it provides you three guarantees. The first thing that it says is that whatever information you send to this third party, it will always keep that private. It would not leak it to anyone. The second guarantee that it provides is that all the information that it has collected over time from different people, we have been sending this globally mutually trusted third party all our information, let's say for a year. All the information that's collected for all these years, it will always keep that private and would not allow anyone to poke inside its state, inside its memory. And the third guarantee that it provides, which makes this particular party very magical, is that it can compute any arbitrary function we want it to compute, as long as we provided enough authorization to be able to compute that function. And it will only output the necessary outputs. Usually, I sort of like refer to this mutually trusted third party as a mutually shared computer. And if you guys are familiar with something called the God protocol, this is the God protocol. This is a picture from Nick Szabo back in 1987. First observation to make is that if we really want these three guarantees if we really want this party to be globally mutually trusted, we want this party to be able to prove these three guarantees to any individual without requiring any additional interaction, which is why we require cryptography. We cannot just make it on certain legal arguments or something like that. We require cryptography for building this globally mutually trusted shared computer. And we started to build Phantom Zone to eventually build the God protocol. But to stick within the realms of practicality, we could only build an abridged version of it. So for the rest of the talk, I will be talking about what is Phantom Zone? Why it is an abridged version of this God protocol. And the second important thing that we're talking about is how can we push the frontiers to eventually build the God protocol? Okay, so Phantom Zone, the abridged version. The key idea in Phantom Zone is something called multi-party fully homomorphic encryption. And for me to describe multi-party fully homomorphic encryption, I'll have to eventually describe you what is single-party fully homomorphic encryption. In single-party fully homomorphic encryption, you have a single client, this guy over here. They hold a secret. They keep the secret private to them. They can encrypt their information, which is A here, with the secret and produce an mp-fhe ciphertext. And then they can send this mp-fhe ciphertext to any server. And the server can evaluate any arbitrary function on their private input, which is A, and produce an output ciphertext. And then the client can receive the output ciphertext and decrypt it. So this is single-party mp-fhe. Coming to multi-party mp-fhe. Well, the key idea in multi-party mp-fhe is that you split this secret, which is held private by a single client in single-party mp-fhe, among many clients. So you have S0, S1, S2 as secret shards split among these three people over here. The first step in multi-party mp-fhe is something called collective public key generation. So all these three parties come together and they generate the collective public key. And then all these three parties, using the collective public key, encrypt their private inputs and produce mp-fhe ciphertext. And then they send their mp-fhe ciphertext to the server. Server executes some arbitrary function on the mp-fhe ciphertext and produce an mp-fhe output. The key thing to notice here is that all these parties would have to produce a decryption share to eventually decrypt the output ciphertext here. So they produce the decryption share using the secret shards, and then they send it to each other, and then only they're able to decrypt the output ciphertext. Because in this case, the secret was split among all these parties. So why is Phantom Zone an abridged version? Well, because Phantom Zone, assuming that in the future we're able to add publicly verifiable mp-fhe to a Phantom Zone, can only guarantee the 3 guarantees that I talk about in the God protocol to only the holders of the secret shards. It cannot guarantee these 3 guarantees to everyone around the globe, which is why Phantom Zone is just an abridged version of it. Okay, so you might wonder, how do we build towards the God protocol? Like, how do we even do it? Well, what I would like to say at the moment is, I would have loved to say that, after a lot of research and a lot of 5 years of research, we have figured out the solution to build the God protocol. But no, there are no enlightening thoughts here. And there's one obvious answer to eventually building the God protocol, which is program obfuscation. What's program obfuscation? Well, to simply describe program obfuscation, let's just assume that you have function f, right? What you can do with program obfuscation is you take this function f and perform some transformations on this function f and produce an obfuscated circuit. You can give this obfuscated circuit to someone else, and program obfuscation guarantees that the only thing that you can learn from that obfuscated circuit is the input to output map and nothing else. Now, you might be wondering, why is this useful? Because if the function is trivial, then you can easily learn it from the input to output map. Program obfuscation becomes very interesting when you sort of obfuscate a program that is a cryptographic function. For example, let's just say that I take a function that decrypts any ciphertext that is encrypted to my public key. Right? So I take a function, and this function has my secret key, and it decrypts any ciphertext that was encrypted to me using my public key. And I perform certain transformations using program obfuscation to this function and produce an obfuscated circuit. I give this obfuscated circuit to someone else. What they can do is that they can decrypt any ciphertext that was encrypted to me using this obfuscated circuit. But they can never, ever learn what the secret is inside that circuit. They can never learn my secret key. And these are the class of functions where program obfuscation becomes useful, and I'll tie it to building the God protocol later in the slides. Okay, so now assume that we can only build program obfuscation for some limited class of functions. Not for general class of functions, but limited class of functions. I'll tell you one way of building the God protocol using program obfuscation. Step 1, modify the mp-fhe scheme that we're using before to become publicly verifiable. What do I mean by that? Well, a publicly verifiable mp-fhe scheme does two things. It evaluates the mp-fhe function, which a normal mp-fhe scheme does. In addition to evaluating the function, it also produces a proof of correct evaluation, so that anyone can verify this proof with the output ciphertext and be assured that the server that sort of executed this mp-fhe function executed it correctly, and which I usually refer to as proof pi of correct evaluation. Step 2. Replace the collective key generation operation that we did in the multi-party mp-fhe with a trusted setup. In the trusted setup, you have arbitrary number of people here. They perform some mp-fhe protocol to produce mp-fhe keys. There are two types of mp-fhe keys which are very important: public key and the bootstrapping key. Bootstrapping key is usually used for some sort of mp-fhe operations that you can completely black box. The key thing here is that no one knows the ideal secret key, because we're doing a trusted setup in MPC to generate these two keys. The third step is modify the trusted setup to also output an obfuscated conditional decryption oracle. Okay, that's a mouthful. I'll sort of go into it one level deeper. What is an obfuscated conditional decryptor? This particular conditional decryptor is an obfuscated program of the following functionality. What it does is that takes an output ciphertext and a proof of correct evaluation of mp-fhe circuit. It verifies whether the proof is valid. and decrypts the output ciphertext if and only if the proof is valid. And this sort of like tells you why did we assume in the first place that program obfuscation may be feasible only for like limited class of functions, because to build the GOT protocol, like to build the GOT protocol using the mp-fhe route, we only need program obfuscation to be practical for this obfuscated conditional decryptor. So we modify the Truxer setup to also output this obfuscated conditional decryptor, and that's it. And another thing to note is that this conditional decryptor also has the secret key, the ideal secret key that no one knows, embedded inside it. Okay, so the end-to-end flow is, you do MPC to generate three things: public key, bootstrapping key, and the obfuscated conditional decryptor, which I now realize is somewhat of a mouthful. I should have chosen some other term. Anyways, the second flow is, now anyone can encrypt their private inputs using the public key, that is the output of the MPC protocol. So you have multiple ciphertexts here. And then they can send it to the mp-fhe server. mp-fhe server evaluates the mp-fhe function, outputs the encrypted output. In addition, it produces a proof because the mp-fhe server is evaluating a publicly verifiable mp-fhe scheme. And then we plugged in the proof as well as the output to the obfuscated conditional decryptor, and the conditional decryptor would only output would only decrypt the encrypted output if and only if the proof is valid. So this is one way of building the GOT protocol using publicly verifiable mp-fhe and program obfuscation for obfuscated conditional decryptor. So there's one way, which I've just shown you, but we need new ideas to push the frontiers and to finally build the to finally build program obfuscation or indistinguishability obfuscation, if you're familiar with that. Here, I've showed you just one way. But if you're able to come up with new ideas, then probably we can make program obfuscation more practical for general circuits, not just for like limited class of functions that we used before. And probably we can directly build the GOT protocol from program obfuscation. Okay, so while I was exploring this field of program obfuscation and I/O, one key observation that I made, was that it's really hard to get efficient program obfuscation from standard assumptions, and we would inevitably require exotic assumptions. And I'll tell you what are standard assumptions, what are exotic assumptions. Well, a standard assumption is an assumption that has been there for a while. For example, D-log, discrete log problem. There also exists additional incentive for people to break these standard assumptions. And exotic assumptions are somewhat newer assumptions, like they have been only there for like 5 years, or not even 5 years, like 2 to 3 years. What we can do as a community to, realizing that we might inevitably need newer assumptions to build practical program obfuscation is we can start examining these newer assumptions, start breaking them, start testing them. Or we can build applications using this assumption so that we can incentivize people to break them and tell us whether they're broken or not. And then eventually, in like a few years, we would have candidate assumptions that are newer assumptions, but they have become then standard, so using which we can build practical program obfuscation. Okay. And taking a first step towards this, we are launching a bounty program for to break one of the candidate assumptions, which is called program obfuscation via local mixing. The way I think about this particular assumption is that they're taking more computational complexity approach than taking like the traditional approach of using algebraic structures to build program obfuscation. The goal of the bounty is that we have provided you an obfuscated circuit with roughly like 240,000 gates, which was obfuscated from an original circuit with roughly 1,000 gates, and you have to find the original circuit. You can learn more about the bounty at offustopia.io. If you know what offustopia is, offustopia means that we're living in a world where obfuscation is practical, and the bounty amount is 10K. And this bounty is launched in collaboration with Ethereum Foundation and 0xSpark. Okay, so before I break, and I think that I have a bunch of time. Okay, before I break, I would want to make one conjecture. And the conjecture goes as follows. I think the God protocol is the convergence of cryptography. Probably building the God protocol would require certain sort of like mp-fhe. That is just one route, but like publicly verifiable mp-fhe and other things like mp-fhe for trusted setup and so on and so forth. But once we have built the God protocol, I think it encompasses everything. It gives us everything that we have been like wanting for a while. It gives us witness encryption. It gives us zero-knowledge proofs via signatures. It gives us MPC, multi-party computation. It gives us FE, functional encryption, and all of these things that we've been demanding for a while. And this is also one of the major reasons that we should start investigating much more seriously how to get practical program obfuscation and finally build the God protocol. And that's it. Thank you.
All right, thank you for the talk. We do have some questions rolling in. Let's go through some of the questions. Let's start with the first one. Can we implement threshold ECDSA with Phantom Zone?
At the moment, yes, because you can express theoretically, yes, but it would be very impractical to implement ECDSA with Phantom Zone at the moment because ECDSA is like you're doing elliptical operations, which is a lot of operations. As far as I understand, threshold ECDSA is possible. It takes 2 days to generate one single signature.
All right, so next question. Can you tell us a little bit more about the definition of obfuscation as a virtual black box? That's the first question over here.
Isn't your definition of obfuscation as a virtual black box impossible? I am not posing obfuscation as a virtual black box. I did not mean to say obfuscation is a virtual black box. By the way, the impossibility result for virtual black box is only for like certain very restricted class of programs. It's not for like general class of programs. Eventually, you can aim for virtual black box with certain caveats. But again, saying that my definition of obfuscation is not virtual black box.
All right. And what can be done today with Phantom Zone?
At the moment, as I said, Phantom Zone is an abridged version of this God protocol. It does not even have publicly verifiable mp-fhe scheme, so it does not give you all the 3 guarantees. The only guarantee that it gives you is that it will execute the function that you ask it to execute while private information can be coming from multiple people. It'll keep the information private, but you'll have to trust it for it. So you have to trust this particular server to always keep the information private and not send it to anyone else.
Perfect. And we do have one last question. Oh, cool. More questions rolling in. Can obfuscating programs undermine open source transparency and make it harder to verify the absence of malicious code?
I see. Make it harder to verify absence of malicious code. Well, that is assuming that the entire program is obfuscated. When I say obfuscation, we require obfuscation for certain parts of the program which can interact with a public program and a private program which is obfuscated. I understand that obfuscation can be used for many malicious purposes as well. Like, for example, like there are several reasons why people might be interested in obfuscation, but we can, as a community, make sure that there's interaction between the public interfaces and the private interfaces which are obfuscated.
All right. And why do you call the publicly verifiable mp-fhe circuit obfuscated? Doesn't the require solidity verifier or something which is public?
No. I think once I give you obfuscated circuit, there are certain guarantees that you can learn from the obfuscated circuit itself, that it does not reveal anything, as long as you've done the obfuscation correctly. All
right. And do you have evidence that the conditional decryption functionality is possible using I/O?
Yes. There are theoretical results, and we're trying to make it practical as well.
All right. Can you give one example each on how I/O can replace ZK, MPC, mp-fhe?
Okay, so for ZK, what you can do is like, you can embed a secret key inside this obfuscated circuit, the God protocol, and a zero-knowledge proof is just a signature from this God protocol. Whatever secret exists inside this particular server or this God protocol or this mp-fhe circuit, obfuscated circuit, a signature by that thing becomes the zero-knowledge proofs. So you do not require zero-knowledge on the client side anymore. For MPC, again, it's a globally mutually trusted third party. All of us encrypt our private inputs with the public key corresponding to the secret key that lives inside this obfuscate circuit. And we send our private inputs to this. It decrypts that, performs some function, and produces the output. So that's one way of replacing MPC, and the same applies for FHE.
Cool. We can stay here for maybe another 10 seconds if there are any new questions rolling in. All right, cool. Let's give